Hello everyone. I just wanted to review generalized linear models and regression for Environmental Science 410 and LRES 510. So regression is a way of taking all our scattered data points and regressing them into one single mathematical equation. And we do that by minimizing the sums of squares, and the method is called the methods of least squares. And there's more sophisticated ways, but I just want to give everyone an intuitive feel about what regression is. And by no means is this teaching regression. So in class we talked about simple linear regression. We talked about the slope of a line y equals ax plus b, where b is the intercept and a is the slope of the line. And so what regression does is fits a line that minimizes the sums of squares, so all the differences on the axis, on the x and y axis, so that when the values are squared, the line represents the minimal difference in the sums of squares. What's left over in the data after the line has been fit is referred to as our residuals. So simple linear regression, where we're using just a simple line where y equals ax plus b, is good for estimating estimating biomass, cover, and diversity responses to the x variable or the independent variable. But it doesn't work well in other cases such as count data, when we have increasing number of integers, or a case where we have only presence or absence, only a binomial response. So when we have the more complicated versions of thinking of count data or presence-absence data, we still have the linear equation beta 0 plus beta 1 times x, the linear line, so like y equals mx plus b, where beta 0 is our intercept and beta 1 is our first regression coefficient. Beta is used to refer to regression coefficients here. But now y is a function of this line. So one useful type of regression that comes up quite often in ecology and environmental science is Poisson regression, and it's log linear regression. So now the natural log of y is equal to the linear equation beta 0 plus beta 1 times x plus beta 2, the second regression coefficient, times x. And so this is often used in count data, density, insects, macroinvertebrates, and all the response variables have to be integers, not 1.5 or 2.5. They have to be a full integer, 0, 1, 2, 3, 4. A good non-biological example is to think about modeling the number of phone calls in a given day in response to the hour of the day. So you can't have 1.5 phone calls or 3.5 phone calls. The number of phone calls increases by integers, 0, 1, 2, 3, 4, 5. And so we've used regression in our homeworks, for example, to model the regression or model the density in response to distance from road of certain flower species. And when we model that in R, we used the generalized linear model formula of density as a function of distance from road, and we specified the family here, or the error distribution, the Poisson distribution. And so when we call up summary within R, we get the summary of the generalized linear model. Here we have our beta 0, which is our intercept, and then we have our slope term, which is distance from road in this case. And the p-value on the far right side there indicates that we have a significant non-zero relationship with p because our p-value, the probability here, is less than 0.05, which is our arbitrary cutoff. So we can take those values and put them into the Poisson equation after we've solved for y, and then we can plot that graphic line. So I won't talk specifically about plotting the Poisson distribution, but we'll skip on to the binomial distribution used in logistic regression. So binomial means nomial is number and by 2, so it means we can only have two values here, 1 or 0. And so now we're using the logit of the mean, and it has a linear relationship to the beta, to the explanatory variables, or the beta coefficients in this case. In this case, we're modeling the probability because we're bound between 0 and 1. So we also performed logistic regression in this class using the formula general linearized model function, and gave it the formula presence absence, where we have data that's either 1 or 0, and using it and we're predicting its response to distance from road again. Now we've specified the distribution to use as the binomial or Bernoulli distribution. We've changed this family equals binomial. And here we have the equation once we've solved logit y for x. So the equation ends up looking like the exponential e to the beta null to the intercept plus the beta 1 coefficient times x divided by 1 plus e raised to the beta 0 plus beta 1 times x again. So here we have our values from our model output, and we have the intercept of 3.9, our beta 0, which we entered here, and then minus this 0.15 multiplied by our x. So if we wanted to solve for specific values of x, we can do that just by plugging in the beta coefficients and seeing what the value of y will be. So here, if we had an x of equal to 0, the value of y is equal to 0.91. So if we were using this to model the distribution of a flower, the probability of occurrence, we would term it here, would be 91%, or 0.91 or 91%. And then if we did the same thing using 45, so 45 meters is the distance from road, we solve the same equation, we get a probability value of 0.04. So R will plot our predicted values for us automatically, or we give it a few lines of code so that it'll plot the predicted values over the range of x. And we did that here, and here you can see, as we talked about before, at 10 meters we have a probability of 0.91 right about here. That looks correct. And then at 45, 0.04. So you can see where the values come from and how we solved for them. So hopefully this clarifies a little bit more how we will use regression, how we use the summaries out of R to understand the responses of certain plant species or biodiversity to our predictor variables. Thanks everyone for listening. Check the homework and D2L for updates.